Swayam Prabha. Digital India. Educated India.
Or it's too complex to kind of track the specific wave function itself and enable so we kind of moved on to density operator, which is basically coming from the projection operator, and we are able to kind of write down the equation of motion, the 191 equation of motion for the density matrix, and also understand explore appropriate Hamiltonians that go into this relevant right? So we have done that. And using those two components, we have developed the so-called optical block equations, which enable you to track various components of the density matrix effectively. We have one of them, interaction with light matter interaction, which is driven by the dipole moment operator, moment which is minus mu dot E, as we know. But the system, as we know, is not isolated, it's kind of interacting with the bath. What the bath is primarily doing is adding a dissipation term. It's driving the relaxation of your photoexcited system. And the relaxation is effectively captured by the so-called collapse operators or Lindblad operators. We have seen two specific Lindblad operators which are most relevant. One associated with spontaneous emission. So you have a photoexcited system, you have an excited state population, for instance, and this excited state population can couple effectively with a bath of photons, vacuum, and transfer its sort of energy, say, and decay back to ground state between the photons. So that's one kind of relaxation or dissipation process, the system, spontaneous emission, which is quantified by an effective decay rate or lifetime. Right? That's one form of it. And here the loss will be primary or only the population, which is basically a diagonal component of the density matrix will be affected by this. We can also have another form of dissipation, which is loss of coherence of diagonal elements primarily, and this comes because of stochastic pattern. You have your prime state and energy state can undergo stochastic inelastic scattering with some path, for example, with phonons or defects or whatever you might think about, some kind of stochasticity in the system, and this stochasticity kind of results in the scrambling of the phase of a coherent ensemble of excitation, leading to the dephasing process. Remember, decoherence dynamics, which is a loss of coherence of diagonal elements going to zero, is driven by both loss of the population in the excited state, so the lifetime of the state, as well as the dephasing processes driven by system bath interactions, stochastic scattering. Okay, so this is kind of overview without any text. I will just spell it out, so that you kind of go and exercise your brain to kind of revise these concepts in your head, or revise them. Okay. What we have not done so far is we have done beautifully everything about system bath interactions in the material, but it's completely irrelevant to us as of now, because we have to kind of sort of take that and infuse it into an observable that we are able to measure in the lab. That's a very important thing. And there, as I've already noted, dielectric response kind of comes into being. We know if I have light-matter interaction, electric field, electric field, classical electrodynamics, it will generate a polarization, right? This polarization is basically thought about as some sort of, charges around your molecule which are sloshing around at the frequency of light, and that's your polarization. And this can emit radiation, right? That's classical electrodynamics. Okay.
Now the challenge now is to link this seemingly classical polarization with whatever we have learned or studied in the context of quantum dynamics. And that will be the focus, because what we want to be able to estimate is that polarization, because that is what we are measuring, especially in a coherent experiment, like for example, pump probe or 2D spectroscopy, so on and so forth, with experiments as well. So the description of nonlinear spectroscopy at the end is primarily rooted in the calculation of polarization. Okay, right there. Polarization is a macroscopic quantity. It's not a microscopic quantity, it's a microscopic quantity. There is a macroscopic collective dipole moment per unit volume. And that's your polarization. So always think of this picture whenever you do nonlinear spectroscopy. You're always thinking of this ensemble, humongous ensemble of chromophones. Now you may ask me, can't I do coherent nonlinear spectroscopy on a single molecule? Let's not get into that discussion for this particular course. That's an interesting question to ask. Let's not ask ourselves that question. But let's say I have an ensemble of molecules, right? And I have an ensemble of molecules. I come with electromagnetic light, electromagnetic field, and of course, it's going to impact the charges surrounding all of these molecules. So what you're going to observe is sort of an ensemble sum over the displacement of all the charges for all the molecules in the system, and that's what gives us the polarization. Sum over all molecules. So your polarization being sum all molecule dipoles mu, so sum over all molecules, m itself is sum over the charges. Okay, that's a microscopic picture. We all know this. And typically, if you remember, again, linear dielectric response, your polarization is proportional to electric field. The proportionality constant is referred to as the linear susceptibility. Of course, this is an approximation. You can always have the higher order terms, which will be the point of this course. Remember also that polarization comes directly from Maxwell's equations written in dielectric media. If you kind of recall your wave equation, polarization exists in your wave equation. I'm just writing this for the sake of completeness. As the fourth term in your wave equation. It's your wave equation. So it acts as a source term, driving the propagation of your electromagnetic wave in your material. So of course, if I assume plane wave-like solutions for electric field, I can also consider plane wave-like solutions for polarization. So polarization, I can write as some amplitude exponential I note, see carefully, I have
noted the wave vector and frequency of the polarization as K signal and omega signal, because the signal is what we are going to measure, the response of the material.
So there is no reason, at least in generic, more generalized nonlinear spectroscopies, there's no reason for you to have single incident electric field. In fact, you will have multiple optical pulses incident on your sample simultaneously, because we are interested in nonlinear spectroscopy. Now, in that case, the final wave vector of the polarization will be kind of on the frequency of the polarization has to satisfy momentum and energy conservation, okay, so-called phase matching conditions, right? So your K signal will be sum over all the input K vectors, and the frequency has to sum over all the input frequencies. This is enforcing energy and momentum conservation. So how do we kind of simply kind of intuitively understand this phase matching condition? The way to think about it is that if I take a single molecule and its dipole, as you know, the dipole will have a sine theta distribution related to displacement of the charge in the molecule, right? And if I take an ensemble of dipoles which have been coherently driven by an external field, the radiation of all this ensemble will only constructively add up along a specific direction determined by a kind of linking a microscopic entity, and you're trying to make an ensemble aberration. Say, okay, this is my direction, specific direction where all the dipole emission will add up to give you a signal. Okay, we'll kind of come back to this intuitive picture later on when we talk about nonlinear optics, specifically when we talk about optical parametric amplifiers, generate short pulses for experiments, which we will do next week. But for now, this is an intuitive understanding. Okay, so now the electric field emitted by the polarization, of course, will have a similar form. So I'm going to unnote that as E signal. So positions. Of course, I'm missing out the complex conjugate. Now, if you take this and substitute back in the wave equation, I'm not going to solve this. I'm going to write down the equation. See, E sig will have I y omega well over MC. Let's say you're going through a medium of some length L. Integrate that for that length. B sine delta K L2 over I delta K over 2. No quantum mechanics here, it's all classical electrodynamics. Few important points. So this is the emitter signal due to this polarization as you have interaction through a medium of length L, and that will, the important aspects is, of course, there are two important terms here. One is there is an imaginary term here, which means the emitted field will always have a phase shift with respect to polarization. And there is always a wave vector mismatch between polarization and emitted field. We'll come back to that later, but these are the few things to keep in fine. Most critical thing is that signal, the emitted feed from light matter interaction is proportional to I times V. That is the important thing. Okay, let's now start trying to do some experiments, right? Let's start doing some experiments. What is experiment? Let's take a material. Okay. And let's say there is an input electromagnetic field. Okay, let's call this K. Linear response. Let's say we are assuming linear response, which means I have linear polarization coming in, which emits radiation. So what I'll have is there is some part of my emission which comes out, some E out, but you'll also have some K signal coming. You generate your polarization medium. I in square. So I out, we already know this intuitively because we know what happens when you send light through light absorbing medium. What happens? Light is absorbed. So I out will be slightly lowered, right? So some I in minus delta I. So again, classically we know kind of how to do this. So I know my absorption, Lambert kind of formalism, is minus logarithm of I out over I in. I am doing this because you might have seen this form already, so it kind of makes it intuitive for you to kind of work through this. So under the weak perturbation assumption, we can say I in is almost equal to I out, which means that it's not very strongly absorbing samples. You don't want to be working with strongly absorbing samples and never see a signal, so weakly absorbing samples. Then you can show that A is in fact almost equal to. So under this assumption, anyway, your I out is E out plus E signal square, because you have two fields. One, the input field has gone out after absorption because you have generated polarization, and this polarization is also emitting radiation. That's your signal, and you know this will be IB square. And I can expand this out, E out plus I chi E in. I have assumed weak absorption, so this will be E in plus I chi E in square. Remember, chi is actually it has a real and imaginary components. So if I make the substitution, you will kind of will see that this will be I in times 1 minus 2 chi imaginary part of the susceptibility plus some higher order components, and it drops out like that. So comparing this equation and this equation, you can kind of see my delta I is approximately to imaginary part of the susceptibility multiplied by input. That's your absorption, classic. Okay, all this is good, but we're still not happy because we don't know what that chi is. This chi is at the moment some response of the material which you can experimentally probably estimate, but it's not giving you a microscopic perspective. You're not linking it back to quantum dynamics. So we need to now bring in quantum dynamics, right? So if you want to bring in that, let's go back to the definition of polarization. What is polarization? is a macroscopic dipole moment. Okay, so when I say macroscopic dipole moment, so quantum mechanically, then how can I define polarization?
By the dipole moment operator.
Dipole moment operator. So what will be the correct quantity that I need to be able to estimate? It is the expectation value of the dipole moment operator that will give me polarization, right? So quantum mechanics tells us the polarization simply expectation value of my dipole moment operator, which we know thanks to density matrices is trace of mu. So, where the time evolution of rho we know how to calculate. We know time evolution is basically driven by your Hamiltonian is h naught minus mu naught e. Right? Here. So we also know from the very definition for linear response, linear polarization, P of omega, this time, this frequency, is susceptibility multiplied by the electric field again frequency. So I can now write from here by taking a magical transform called Fourier transform. I can write P of t time domain this is basically a convolution integral. Basically, that means that the system response, the polarization, depends not only on the instantaneous electric field, but also its time evolving behavior driven by causality. Right? Come with an electric field at t minus tau, and then at a later time, my polarization is affected by the instantaneous response, kind of capturing that aspect of it. So R of tau, this is a very important quantity, This is what we will be calculating for all our nonlinear response functions. This is called impulse response function. Okay, sort of an inverse Fourier transform of your susceptibility. It, as kind of noted, it quantifies the influence of the field at t minus tau on the system at a later time t. Kind of tells you the memory, which is then driven by the system dynamics, by interaction driven. Okay, so now we have this. So now we need to be able to relate these two formulas, right? So that I'm able to write my response function in terms of my quantum mechanical operators. Okay. So remember, technically, this is all written in the interaction picture. Let's not forget that. Everything has been developed in the interaction picture. So let's say I'll go back now, expand that out, explicitly writing it in the interaction picture. P of t raise mu I, so interaction picture, dipole moment operator, and dropping operator. There. So I, let's say I'm only interested in the first order polarization. This will be first order. Now we know, we have already seen in one of the early classes how we can write a perturbative expansion of the density matrix and the first order term in the perturbative expansion, again in the interaction picture, given by E1, let's call it Pi, the interaction potential, transformed, and let's call time 0 kind of density matrix, your starting point as an equilibriated density matrix. Remember, what we are trying to do is get a form for our response, impulse response function. That's what we are hoping to get. So let's substitute this into this, so we can get my first order polarization, trace I of t minus I over h cross t prime minus mu I prime prime reorganize this cross integral prime out prime becomes trace of mu I of t multiplied by mu I t prime put this out, put this in side. Now pull the integral out of the trace. That's what I did. Okay, now I can make a substitution. It's a bit of math. You can see my notes if you're interested. I'm going to say t tau as t minus t prime, and I will use some relationships, commutator brackets. I over h cross integral 0 to infinity tau e of t minus tau raise mu I tau mu I 0 okay. Now if I compare this equation with the previous equation that I had, if I compare this equation with this equation here, you can derive expression for the impulse responsive function, impulse response function tau to be I over h cross trace of mu I tau mu I 0. So, and to preserve causality, I'm going to introduce a Heaviside function here. Heaviside function simply is 1 only if tau is greater than 0. 0 if tau is less than 0. Want a response before the pulse arrives. That's why we enforce causality through this. Okay, very important expression. That's the response function. Remember, this is all first order response function. It's kind of elegant form. It's basically proportional to the trace of mu I at tau and mu I at 0 multiplied by the initial condition of your density matrix, right? Kind of an elegant form. I'm going to make it even more elegant now, but at least I claim it to be more elegant. I'm not going to show this, but I can rewrite my response function can kind of go and check this yourself. I over h cross theta of tau multiplied by two functions c and its complex conjugate c of tau trace mu I tau I of 0 real c star is of course complex conjugate trace I tau real I of 0. So look carefully. For example, look at this function. Okay, look at that function. Can you say what that is? You're taking a trace of a function multiplied by a density matrix. It's an expectation value, right? It's expectation value of what? A product of two operators, dipole moment operators, acting at two different times. It's kind of correlating the two functions. Okay, so this is referred to as a correlation function, C of tau. So it's kind of what C of tau is telling you is it informs of the memory of the event. It's again the same thing. Okay. Later on we will see it kind of appears in the fluctuation dissipation theorem, which has a lot of consequences in system bar interactions. But for now, it kind of enables us to kind of keep it very simple. Your response function given by this equation, I over h cross, Heaviside function for causality, multiplied by C of tau C minus C star of tau, the complex conjugate, whereas C is simply the expectation value of the product of dipole moments. Very simple to kind of, and elegant to kind of. So let's keep this the back of our head. We'll come back to it later. In fact, at the end of today's class, we are going to kind of see what is referred to as diagrammatic expansion. We're going to write double-sided Feynman diagrams for interaction, and these correlation functions comes very handy and gives you a very physically intuitive picture and given representation by enables you to quickly write out all possible excitation pathways, even having 10 possible So we'll come back to that. Keep this in mind. So this is a response function. At the end, this response function will enable you to calculate polarization. And this is the heart of it. So this is where your Horn dynamics are coming. Okay. Cool. Okay. Now let's go back to two-level system. Okay. Two-level system. Let's explicitly calculate the linear response for a two-level system. Linear response. So I can write my optical block equations, which we all know very well. I'm only going to write off diagonal element for now. Zero. Remember that this is sort of a simplified version of what we have seen in the last class. This is more phenomenological kind of version, but we have kind of seen already that even doing a more complex flat form kind of remains similar, not that different, and you have some relaxation damping parameter here. Okay. Now we can solve this under some initial conditions being everything is in the ground state, nothing in excited state, so on and so forth, and you will see this the e power minus I naught minus e1 cross power minus gamma t 0, 0. Should be a t here. Yeah, we have an identical. Now, this is a generic solution. Let's say we take a very specific scenario. Very specific scenario where there is nothing happening till t equal to 0. At t equal to 0, I come with an impulsive excitation. Nothing happening till t equal to 0, and at t equal to 0, I come. This basically kickstarts a time evolution of my off-diagonal element. Of course, the initial starting point at time 0 will be proportional to mu 1 0, the transition dipole moment strength, which is the interaction. And let's say we let that system evolve in time, and later at a given time t1, this polarization that I'm going to create is going to emit a light field. If I do that, my impulse response function now, first order impulse response function, will be proportional to mu 1 0 square e power minus I e1 minus e0 over h bar e1 e power minus gamma e1. Later on, we will derive this more explicitly. Diagrammatic expansion makes the life simpler. So wait till that point if you don't completely comprehend how we got this expression. And accordingly, your polarization now, first order polarization, will be minus I over h cross equals 0 to infinity t1 e of t minus t1 first order impulse response function t1. That's your polarization, time evolving polarization. Right? So now if I consider a situation where my E of t is E naught of t e power minus I omega t plus e power I omega t. Let's say omega is resonant, so we are going exactly on top of the resonance. Then you will see my P1 of t polarization. Calculate this to be minus I over h cross mu naught 1 0 over I omega t infinity 1 e naught t minus 1 e power minus gamma 1 minus I over bar mu 1 0 square minus plus omega t 0 to infinity 1 e naught t minus t1 e power minus gamma t1 or minus 2 omega t1. Now we have seen something like this. We have something which is oscillating at twice the frequency, the other not. So we'll make the famous or infamous rotating wave approximation. And let's say we assume a delta excitation, which means E naught t is E naught e power I omega t multiplied by delta function. Then your polarization will be minus I over h bar E naught 0 square e power minus I omega naught t. Omega naught is simply the transition. Don't need omega naught.
multiplied e power minus gamma t. So this is what is referred to as the free induction decay. What free induction decay means that you have a two-level system. I come with electric field, impulsive excitation, so delta function, boom, and it generates coherence, and this coherence will evolve in time. If you look at this, there are two things. It's oscillating at the frequency of omega and decay at the rate of gamma. Right? So you will have something which is oscillating and decaying. That will be your polarization. This is in time. Does anybody know if I take a temporal profile like this and do a Fourier transform, what would you get? Too much detail to ask.
Aperture, slit.
Slit, no. So it happens to be a Lorentz. So, of course, if you have non-damped oscillation, you get a delta function in Fourier transform. If you damp it, you get a alignment with a Lorentz transform. In fact, if you take this Fourier transform it, you get a Lorentz. Okay. Linear response, we have done it several times in different methods, starting even from wave functions, density matrix. So you might ask, come on, man, let's go a bit more deeper. We already did this in several iterations, several forms. So let's tackle the elephant in the room, which is a nonlinear polarization. So that's why you're all here, right? Okay. So in nonlinear polarization, we know this. This is the most generic one. We have zero order to this. Going order, so on and so forth. And we know now that these polarizations given by the trace of the product of dipole moment and the density matrix in the interaction picture. Always don't forget that. So on and so forth. As rho n is an nth order expansion of the density matrix. What you have, rho 0, 1, is just the equilibrium of the initial condition of your density matrix. Rho 1, interaction picture, minus I over H cross, and minus infinity E, dt, di of 1 here, dt1, know this. So what we are doing here, time axis, okay, at some t1, we are coming with our potential. Let the system evolve and measure or observe at some time t. And of course, when you do this, you're integrating from minus infinity, observing to that point. Second order expansion. Similarly, minus I for h bar square integral minus infinity to t
2, time ordering is important. 2, 1, have a nested commutator now. I 2, I 1, 1, 2, 3. What we are doing here, stay E1 coming with an interaction and let the system evolve for some time, and then come with another interaction, let it evolve for some time, and T observe. Okay, so now we want to calculate nonlinear polarization. So let's calculate second order nonlinear polarization. For calculating second order nonlinear polarization, just have to solve this. You have second order impulse response function and 2 electric fields. If there are no 2 electric fields, there is no second order polarization. There has to be a 2 field interaction, which I am going to call TE1 and E1 comes first and then E2 comes later. And we know this has to be equal to the trace of mu I of T rho I 2 T. It's a bit of a derivation which I am going to skip over now. Like same way last time we did, we have to do some substitutions. I'm going to write down the expression for second order impulse response function, because that is the one which ties our system to our observable to the quantum dynamics in the material. Second order response function I h bar square. I have 2 Heaviside functions here. Multiplied by trace I tau 1 plus tau 2 mu I tau 1 mu I tau 0 multiplied on unity matrix. Okay, so now I can expand, I can generalize it further. But again, remember in the first order response function, we are able to elegantly write it using correlation functions. Correlation functions gives you the illusion of how the system kind of chooses the memory. And that is all in the expectation value of the correlation between dipole moment operator at 2 different times, which is the memory part. So accordingly, we should be able to expand this. It so happens you cannot use simply one correlation functions. You need to have multiple correlation functions. For second order, you need 2 correlation functions. And you can show that your R2 is I over h bar square theta of tau 1 of tau 2 sum over alpha 1 2. I'm going to call these correlation functions for the second order as Q 2 minus Q alpha star tau 1 tau 2. Okay, so just response function. What are Q1 and Q2? Again, like the previous case, they are trace of a product of density matrices applying or on the product of dipole moment operators, sequence of dipole moment operators acting on the density matrix at the end of the day, right? Now, those are the correlation functions because at the end expectation value is trace of bunch of operators multiplied with density matrix, right? So your Q1 in this case, trace will be 3 dipole Q1, Q2, slightly different. That's where a lot of things are given. If you look at trace, kind of examine this, they look almost identical, but they're not identical. There are different terms in the law of response function, which basically accounting for different permutations of interactions at different times, basically. Right? In another word, it's kind of accounting for whether an interaction is happening. So if I have my density matrix matrix has a ket and bra part, right? So I can make that operation either on the bra side or the ket side. I'll show you how that is going to come up explicitly now. But basically, at which part of this density operator am I acting on with my interaction basically determines different pathways, and that's what these correlations pertain to. I'll show you that explicitly. Might sound all Greek to you, so let me explicitly show you what that means. Let's take term 1, which is Q1. This trace mu I tau 1 plus tau 2 mu I tau 1 mu I of 0 to equilibrium, right? Now we are in the interaction picture. Let's go back to Schrodinger picture for a moment. If we're going back to Schrodinger picture, what do I need to do? Let's find this out. So this one is expanding this, right? You know how to go from interaction Schrodinger pictures. Similarly, you can do the same thing there. No, I didn't make a mistake. Good. That will be not dagger. Now 1 mu not now 1. Expanded this part in the Schrodinger picture like this. Of course, at time 0, there is no time evolution happening, so Schrodinger interaction pictures are going to lead to the same mu. I'm going to leave mu I of 0 to be mu times. Now I can apply some cyclic properties and kind of simplify this further. I'm going to write down the final expression. You can see my notes for kind of detailed derivation there. So I can, trace has cyclic properties, so I can cycle the things and reorganize my operators within the trace. So this will be mu naught tau 2 mu naught tau 1 mu equilibrium naught dagger 1 dagger tau 2. Looks cumbersome, but there is some elegance in this. Let's go over this. Remember, for example, this could be starting out to be like this, right? If you are in the ground state, that will be a starting point. Okay. So what you are doing, your first step, what you are doing here, if I take this my starting point, you're taking the dipole operator and acting on it on the bra side. Right? Agreed? So your first step is dipole acts, sorry, not the bra, ket. So on the ket of rho equilibrium. Once you have that done, what you are doing is you are evolving it. Evolving the system till or during tau 1. So that's the second part. Second part is you evolve under what? Under H naught. Because that's the time evolution operator is of the system. Under H naught, which will have all its bar interactions in it, right? H naught, we typically assume it to be not having bar interactions, but if I want rigorous it, I should have system bar interactions as well. Not like matter, system bar interactions. Okay? During tau 1. I evolve it, I evolve this, and then act again, mu, again on the ket side. Dipole acts on the ket. Once that is done, so you act a dipole, evolved it, act another dipole, you have another evolution. Another time evolution. So you are again evolve again under H naught during tau 2. Once that is done, so you have finished your field interactions. Lastly, you have to measure the polarization that's done, or the field emitted by the polarization. For doing that, you still have to multiply it by like matter interaction because that will tell you strength of the field which is emitted. So you multiply by the dipole moment operator and trace it out. The fifth step, final step is multiply by mu and trace. Okay? Makes sense? Makes sense? So this is basically like matter interaction for nonlinear spectroscopy in a nutshell. If you kind of get intuitive picture of this, that's more than enough. That's all you do. You come with a dipole. You in this case you're acting on the ket. In the other term you act also on the graph, for example. Then you time evolve under it. Then you come with another field. Then you time evolve. If you have only two fields, that's evolution. Then you are measuring polarization, you multiply it by your dipole, trace it out, that's your polarization or signal limit. Make sense? right? Okay, good. So I can kind of also make it even more compact, this expression. I can define a super operator called G, be acting on some AB, U naught, dagger. If I do this, then you will see my Q1 simply becomes trace of mu G of tau 2, mu G of tau 1, mu. So as you can see, in Q1 case, this is what is referred to as ket interaction. For this particular case, we're acting only on the ket direction. Okay. And I think if we expand this out, similarly for Q2, and Q2 happens to be a ket bra interaction. Basically, you need to expand out the trace, reorganize it, get the Schrodinger picture, and suddenly this comes. Okay, so let me kind of summarize that. So remember, I have also Q1 complex conjugate of Q1 and complex conjugate of Q2. So you have 4 terms, 4 correlation functions. So your Q1 is a ket interaction. Your Q1 star, of course, will be a bra interaction. Q2 is a ket bra interaction. Q2 complex conjugate will be a bra ket interaction. Okay. Now, at this point in time, if this is all troubling you, kind of confusing you, hold that. This is basis. I want to write out the expression for third order as well, and then we take a break. After we come back and break, we use double-sided Feynman diagrams. And once we get double-sided Feynman diagrams, this will all become so good to us. At the moment, it's all probably confusing, but it will all become easy. Okay? Alright. Another important thing to remember, usually in spectroscopy of material systems, we do not care about the second order response. Any guesses why?
That needs symmetry.
So, if most of the systems have symmetry in them, and if you have symmetry, there is no second order nonlinearity. Kind of isotropically goes away. There are some specific cases where there are interesting stuff happening. For example, in some emerging quantum materials, correlated materials, when there is some kind of ordering happening, there is some kind of symmetry breaking happening, and that symmetry breaking will drive generation of second order nonlinearity. And this is a very growing, emerging interest in quantum materials where they want to use the second order response to capture those parts. Okay, so it's kind of has some relevance, especially emerging quantum materials, but in most of the cases we will not be talking about second order responses. What is more relevant is something which is easily available to you, is a third order response. So let me write down the expression for third order response. Third order response are three field interaction now. There are 3 field interactions, which means 3 different interaction times. Tau 1, tau 2, tau 3. I, H bar, Q. Trace of I, tau 1. 3 for interaction. Second interaction, tau 1 plus tau 2, followed by first interaction. It's not followed. It happens first, but I'm writing it in that way. Final term. Implied kind of messed up the brackets. I don't need to worry about this complex looking form because I know I can rely on correlation functions. I can write down correlation functions. That will exist. Causality is important. We'll have 4 correlation functions. R1, R2, R3, and R4. And there is a convention here. Remember, there are specific direction of interaction acting on ket or bra. There is a convention. R1 is always ket interaction. R2 is always bra interaction. R3 is always bra ket. R4 is always ket bra. You don't need to remember all of this. It naturally flows out in the double-sided Feynman diagrams, but for the sake of completeness, I put it there. So happens all your 2D spectra is what we want to kind of understand either in R2 or in R4. The compromise. Also the impulse response functions that we need to do. Now, I'm sure you are all exhausted by looking at this complex looking nested commutator brackets and dealing with all these cyclic relationships moving around and kind of finding correlation functions. I agree with you, it's kind of complicated. So let's take a break, and after the break, we will use a very beautiful way of simplifying the problem using double-sided Feynman diagrams or ladder diagrams. I personally like double-sided Feynman diagrams. And note, these are not technically Feynman diagrams, but double-sided Feynman diagrams, I would say probably the person who kind of used it for the first time invented it is Charles Mukamel. He should get the credit for this. He has many other diagrams which he uses all the time. But I think it's called double-sided Feynman diagrams, but it has nothing to do with the actual Feynman diagrams. Just a note there. Apart from the fact that there is interaction. Develop what is called diagrammatic perturbation.